Hi everyone, my name is Pradyumn Kejriwal and today we will discuss the 10th problem from the CP sheet by TLE Eliminators under the rating of 1400. So let's begin. So as you can see I have my sheet right here and I'll open the problem. Alright, so it is called Make It Round. Inflation has occurred in Birdlandia, so the store needs to change the price of its goods. The current price of the good N is given. It is allowed to increase the price of the good by k times, with k less than equal to m and greater than equal to 1, where k is an integer. Output the roundest possible new price of the good, that is, the one that has the maximum number of zeros at the end. For example, the number 481000 is more round than the number 100010, because there are 3 zeros at the end of this number but only 1 0 at the end of this number. If there are several possible variants, output the one in which the new price is maximal. If it is impossible to get a rounder price, output n into m. Okay. So what they are saying is that we have to, basically currently we have been given a number n and a number m. Okay. So the current price of a good is n, and we can multiply a k into it. We can multiply it by k, where k is between 1 and m, such that this final price is the roundest possible. It is the roundest possible. That means that it should have the maximum number of trailing zeros. Maximum number of trailing zeros. Right. And what they are telling us is that if there are several possible answers, then output the one in which the new price is maximal. So we have to output the maximum value of n into k if there are multiple number of such possible variants, right? So for example, we have the samples like 6 and 11. Okay, so n is given to be 6 and m is given to be 11. So basically we can choose any k which is less than equal to 11 and need to multiply it into this n. So let's say if I choose k equal to 5, okay, then I will have n into k will be 30, right? So it has one trailing zero, so that is fine. But if I multiply by k equal to 10, right, then my n into k is 60. Okay, so this one also has only 1 0, but since it is larger, this one is an answer. And because we cannot get two trailing zeros, you will see that in later, but because we cannot get two trailing zeros, that's why the answer is 60, because with one trailing zero it is the maximum, right? Then for example, we have 5 and 43. So in this case, n is equal to 5 and k equal to 43, m equal to 43. So we can select any k which is less than equal to 43. Okay, so here in this case, what you can do is select k equal to 40. Okay, and your number will be n into k, which is 200. So here you are getting two trailing zeros, right? And that is the maximum that you can get. Okay, so that's why the answer is 200 to this one. All right, and the constraints here are that the n and m can go up to 10 to the power 9, right? N and m can be up to 10 to the power 9, right? And also the test cases are 10 to the power 4. Okay, so basically you cannot really do O of n or O of m solutions, because in 1 second you can only pass 10 to the power 8 operations, right? That's why this is not possible, because you have a t also with this. You have n into t, and that will not pass because it is 10 to the power 13, right? So if you try O of 1 into t, or O of log n into t, that will pass, because this is 10 to the power 4 only, and this is 20 into 10 to the power 4 or something, or 30 into 10 to the power 4, right? So if you can do it in log n or O of 1, then that is fine. right? So now at this point, you can try and pause the video to solve the problem by yourself. Alright, so I'm assuming that you have tried the problem by yourself and you want the solution now. Okay, so basically, let's just focus on what we want. Okay, so we want that in the number n into k, the number of trailing zeros is maximized, right? That is, whatever k we choose, like we can choose the k, n is given to us, but we can choose the k so in such a way that the number of trailing zeros is maximized. Okay, so how do we choose the optimal k? To think about that, let's think about this part, the number of trailing zeros. Okay, so in a number, let's say if I tell you that a number has two trailing zeros, let's say this number 2300, two trailing zeros, that means it has two tens as a factor, right? That if I want one trailing zero, I will need a 10 in the prime factorization, and if I want one more trailing zero, I'll need one more 10. So this number has 10 to the power 2 in its factorization, right? So that means it has, like, I can write this 10 as 2 into 5, right? So basically, if a number has two zeros at the end, then it has to have 2 to the power 2 and 5 to the power 2. Or in general, if I say that if a number has d zeros at the end, d zeros at the end, I mean d trading zeros, then it has to have at least 2 to the power d and 5 to the power d as its factor. Okay, so that is one thing that is very clear to us. Okay, so basically, in my n into k, let's say I want the power of, I want the number of trailing zeros to be d. So in that case, I will have to have at least d powers of 2 and d powers of 5 in this n into k number, right? So if my n has enough already, like let's say if it has already at least d powers of 2 and d powers of 5, then whatever k I'll choose, this n into k will definitely have at least this much. Whatever k I choose, doesn't matter, right? But if this n does not have enough number of d's, enough number of 2's and 5's, then I will have to use this k and ensure that this k has those missing 2's and 5's, right? So like if n has, let's say n has 2 to the power a and 5 to the power b, and let's say they both are less than d, that is the 2's and 5's are not sufficient in n. So in that case, our k has to have at least 2 to the power d minus a and 5 to the power b minus d minus b. That is, if we need d powers of 2 and n already has a powers of 2, then we need d minus a more powers of 2. And if we need 5 powers of d powers of 5, and if we already have b powers of 5, then it needs d minus b. So if I give an example, like let's say our n is given to be 2 power 3 into 3 raised to power 7 into 5 raised to power 5, and we need 6 zeros at the end of n into k. Okay, so okay, this 3 power 7 is just irrelevant because the number of 3's does not affect the number of trailing zeros. Okay, so we can ignore that part. But okay, now if we want 6 trailing zeros at the end, so that means that we want 2 to the power 6 and 5 to the power 6. So if we already have 3 2's, that means in my k I will need 3 more 2's. And if we already have 5 5's, then I will need one more 5 in this. So k has to have at least this much. Like k can be a multiple of this number, but it has to have at least this much as a factor, right? It might have more 2s or more 5s, I don't care, or more even 7s. Like, doesn't matter, but it has to have at least this much. So that means that k has to be a multiple of this much, or in this example, in this case, 2 to the power 3 into 5, that is 40. So k has to be a multiple of 40 if we want at least 6 zeros for this n, right? Okay, so this is fine. So now what I can say is that k has to be this much, but okay, our range is from 1 to m, right? Like our valid range of k is 1 to m. So if we want 6 zeros, we can choose any k which is a multiple of 40, but it has to be less than equal to m, right? So for example, if we have m equal to 100 and we want a multiple of 40, okay, so we can take either 40 or 80, right? They are both multiples of 40 which are less than equal to 100. Okay, but what will we choose then? So we will choose this 80. Why? Because they have told us that we need the maximum possible price. I mean, if there are multiple possible in which the number of zeros is same, then we will print the maximum possible price, right? So we will take k equal to 80, right? So basically our problem has now become what? That k has to be multiple of 40 and it has to be less than equal to 100. So basically we have to find out the highest multiple of 40. I mean, for this example, highest multiple of 40 which is less than equal to 100. So that's what we found out, that's 80, right? But in general, let's say we have n equal to 2 to the power a and 5 to the power b, and we want, let's say, d zeros. But okay, what about this d, guys? Like, we don't know this d. I'll tell you later. Okay, but for now just assume that we want d zeros, okay, in my number n into k. I mean at least d zeros. Okay, so if we want at least d zeros in my number n into k, then I will need 2 to the power d and 5 to the power d. And if we already have in my n a and b, then in my k I need at least 2 to the power d minus a and 5 to the power d minus b. So let's say this number is capital K. Okay, this number is capital K. So I basically want that my small k should be a multiple of capital K. A multiple of capital K. Okay. So essentially we want to find out the highest multiple of capital K which is less than equal to m, right? Okay, but what if m is too small? Like, what if our value of k is 5, that is we want a multiple of 5, but our m is equal to 3, that is our range is just 3. In that case it is not possible to make d zeros, right? Because there is no multiple of 5 which is less than equal to 3. Okay, so if m is greater than equal to k, then only I can get that, right? So if m is greater than equal to k and we want the highest multiple of k which is less than equal to m, right? So just by example we can understand that. Let's say capital K is equal to 4 and capital M, I mean small m, is equal to 13. Okay, so in this case what's the answer? It is 12, right? I have 4 here, I have 8 here, I have 12 here, and I have a 13 here. So this 12 is the highest multiple of 4 less than equal to 13. So in general, if we want to find out that what is the highest multiple, we can simply subtract this remainder from m. Like, if we want that it is a multiple of k, we can simply subtract the remainder upon dividing by k. So if we subtract the remainder of k, like of m divided by k, from this m, then we get the highest integer divisible multiple of k less than equal to 13. So like in this case, you can see that 13 if we have, so we want the remainder is what, 13 mod 4, which is equal to 1. So if we just subtract 1 from 13, we will get 12, right? So we will get the highest multiple of k, which is less than equal to m, right? So basically we now got that what is the highest number, like sorry, we got that what is the answer if we want at least d number of zeros. Like if we know that how many zeros we want, then we can easily find out that can we do it or not, and what is the highest number that we can achieve with at least d trailing zeros, right? So we found out that can we make d zeros or not, right? We found out that. Now we can simply just brute force all the possible values of this d, right? Like basically we want the maximum value of d, right? The maximum value of d. So we can simply iterate in backwards. Like I'll simply start iterating from 18 and down to 0, and I'll just check that, let's say, can I make 18 zeros, can I make 17 zeros, can I make 16 zeros, and so on. So as soon as I can make a certain number of zeros, I'll just print that out, because that is the maximum number of zeros that I can get. Like greater than that, we already checked, it is not possible. If we are iterating in the decreasing order, then we have checked that, okay, can we make 18? No, we cannot make 18. Can we make 17? We cannot make 17. Can we make 16? Yes, we can make 16 zeros. So in that case, we'll just print that number with 16 zeros, because we have checked that we cannot make 18 and 17. And you might think that, why am I starting with 18 only? Like why 18? What about any higher number? Is it impossible? So yes, the answer is that the maximum possible number of zeros is 18, because the constraints here say that our n and m are 10 to the power 9 only, right? So the maximum possible value is n into m, which is 10 to the power 18. 10 to the power 18. So if you have more than that, like if you want 19 zeros, then that is at least 10 to the power 19, right? So that is not possible to make. So that's why the maximum number of zeros that you can make is 10 to the power 8, I mean 18 zeros. So you can just check for every value of d, that can we make 18 zeros, can we make 17 zeros, can we make 15, 16 zeros, and so on. And as soon as you find that this capital K value is less than equal to m value, that is, it is possible to make that many number of zeros, you will just print that value and you will break up the loop, right? And that's the entire solution. Okay, so yeah, so now we can like see a test case. So let's say we have 6 and 11. So 6 is what, 2 into 3, 2 power 1 into 3 power 1, right? And m is given to be 11. Now what we want, let's say if we want 2 zeros, d equal to 2, right? Then we basically want 2 to the power 2 and 5 to the power 2, right? But this has only 1 power of 2 and no 5s, right? This has 5 to the power 0 basically, so it has no 5s. So in our k, like for our capital K becomes 2 to the power 1 into 5 to the power 2, because we want 1 more 2 and 2 more 5s if we want 2 trailing zeros, right? Because we already have a single 2. So this is what, this is 50, right? But our m is just 11, so we cannot have a multiple of 50 for our small k. So d is equal to 2 is not possible. What about d equal to 1? For d equal to 1, we need 2 to the power 1 and 5 to the power 1, right? And we already have 2 to the power 1, right? So we just need 5 to the power 1. 5 to the power 1 we need. So basically our capital K value is 5 to the power 1. and our m is equal to 11. So we want that what is the highest multiple of capital K, which is 5 less than equal to 11. So what we'll just do is 11 minus the remainder of 11, which 5. So that is 1 minus 11 minus 1, which is 10. So our value of K, optimum value of K is 10. And final answer is n into K. N was 6, right? N was 6. So n into K is 60. Okay. So that's the entire solution. And I ran it on this test case. Like I started with d equal to 2 because I knew that the answer is less than that. Like I just, to show you that what will happen if you take too large value, I started with d equal to 2. But your code will start with d equal to 18 and move down the way, right? So yeah, that's the solution here, and I'll just show the code now. Okay, so here is the code. So in your main function, you have p2 equal to 1, p5. Okay, so what I have done here is I have stored the powers of 2. Like I have these two arrays which stores the powers of 2 and the powers of 5. Like 2 to the p2 of I is basically 2 to the power I. I am storing the powers of 2 and powers of 5 up to 18. Okay, I have used them ahead, so that's why I have saved them. So I'll initialize them in this main loop. So 2 to the power 0 is equal to 1 and 5 to the power 0 equal to 1. Now for int I equal to 1, I less than equal to 18, I plus plus. P2 of I equal to 2 into P2 of I minus 1. So 2 to the power I equal to 2 into 2 power I minus 1. And 5 power I is equal to 5 into 5 power I minus 1. And then we solve test cases, right? Int t, c int t, while t minus solve. And in my solve function, I have taken nm, c in nm. Now what I am doing is, I am counting that how many 2's and 5's does my number already have. Like in this case, it has a single 2 and no 5's, right? So I'm just calculating that. So C2 is that how many 2's this n has, and C5 is how many 5's this n has. So our temp is equal to n. While temp mod 2 equal to 0, we will do C2 plus plus. Like while our n is divisible by 2, I will divide it by 2 and I'll increase the counter, right? So I'm essentially decreasing the number of 2's by 1. So while it has a 2, I'll do this. And same thing, while temp mod 5 equal to 0, C5 plus plus and temp divide equals to 5, right? Now I will just check for like that thing from 18 down to 0, right? That can we make these many number of digits. Okay, so extra 2 and extra 5, that if I want these many number of digits, how many extra 2's and extra 5's do I need, right? So extra 2's is basically if I want dig number of zeros and I already have 2's, then I want dig minus C2 extra number of zeros. But since it can be negative as well, like since it might be possible that my C2 is already greater than number of digits, that is I already have enough number of 2's, it can be negative as well. So I'll take the maximum with 0. In that case, we need 0, right? We don't need anything extra. And for extra 5, same thing, max of 0 comma dig minus C5. Now if this number, capital K, this is my capital K, 2 to the power extra 2 into 5 to the power extra 5, if that is less than equal to m, that means it is inside the limit, then we can make this number of digits, like this many number of trailing zeros we can do. So the largest K we'll find, that is m minus m mod capital K, right? And we'll just print largest K into n. That is the final answer, n into K. And also I'll multiply 1 LL because it can overflow inside the integer range, right? And we'll just print that and we'll return, right? So that's the entire solution, and it will take O of log n time because see, this is one loop. It is counting the number of 2's, and the number of 2's is just O of log n, and the number of 5 also is this number of O of log n, sorry. And this 18 down to 0, that also O of log n, right? Because it was 10 to the power 18 maximum, so we did 18. So basically it is log n. If it was 10 to the power n, then we would have taken n as the upper limit. So it is O of log n. So it is O of log n time complexity. And for space complexity, like I have stored the powers of 2, right? Powers of 2 and powers of 5. So they take O of log n space, and that's why the space complexity is O of log n, right? So yeah, that's the entire solution for you guys, and I hope you all understood. And thanks for watching.